And it also so February has turned into a little bit of a ionospheric or atmospheric physics month. So this is a good segue into some atmospheric physics. So I will hand over to
Thanks, Justin. Thanks very much for inviting me, and thanks for coming along tonight, folks. I've been fascinated by WSPR, or the digital modes, for quite some time, and I love WSPR because there's a huge database there that goes back to 2008 or thereabouts, and I've been sort of mining it. And I have had a long-term interest in solar flares and auroras and things of the upper atmosphere, and you can use that or use WSPR to sort of study some of these things. And I'll show you a few little projects I've been working on that deal with some of those topics. And if anybody's interested, would like to follow up some of that, I'd be very happy to even share my code and analysis stuff freely. So please let me know if you're interested. But a lot of these things you probably know as radio amateurs at HF and VHF, the effects of solar flares on propagation, auroral events, solar proton events, and the like. And I'll go through a few of those. And then at the end, I'll show you something on just started to look at the other night when Justin prompted me, which is tropospheric propagation. So I'm going to talk about these things in order. So I've used the WSPR database and some other data sets to have a look at the effects of solar flares on propagation, mainly at HF. Sporadic-E on 6 metres and 2 metres in particular. Trying to understand, Sporadic-E is one of those topics that still has some science questions associated with it. What is the mechanism producing Sporadic-E? HF auroral influences, so looking at high latitude propagation, and solar proton events, those really big solar events that cause absorption in HF in particular. So, large solar flares. So you probably know that when we get a big X-ray flare from the sun in the daytime hemisphere, the D region absorption goes up and you lose your signal. So what I've done is I've mined the WSPR.live database, which I don't know if anybody uses. It's a great database that you can query quite selectively, and I've picked out the VCO region spots there. I've got some solar flare data from NOAA, picked out the largest flares. So these are the X-class flares. You might have come across these, the biggest solar events, and there are about 139 of those in the daytime in the VK region since 2008, and I've looked at some short paths. And that's just an example there, just showing you that, when you get these big flares, and the red line there is, I've composited the number of WSPR spots at the peak time of the flare. Not unsurprising, when you get a big flare, the WSPR activity drops out. Folks are just unable to communicate. It's the D region absorption that's...
What's the scale across the bottom?
Yeah, so that's in minutes relative to the flare peak. Sorry, the numbers are a little bit small here, but they're 25-minute intervals here.
So I was going to ask the vertical scale.
Yeah, the vertical scale is it's the relative number of spots. It's scaled. This is essentially 1 to 0. So it's scaled relative to the maximum number, which is the pre-flare number in the case of that one. It's actually the second one here. So it's kind of just shows you the relative drop-off in the number of spots. And you can then, slice and dice this according to signal-to-noise ratio and a few other things. But this was the simplest thing that I could do. But it just shows you basically when you get a big flare at 20 metres, something like 70% of the spots drop out or so. Now these are, as I say, the largest flares. So kind of, haven't sliced and diced according to the maximum intensity, which is another thing that one could do. But I mean, this is the sort of thing that you probably know quite well. during solar flares, but it's just kind of one of those things that having a long database, you can start to build some statistics with a large number of different flares, and then you can probably get into that in a little bit more detail, which I have done here. So a little bit hard to see on the left-hand side here, but these are, this is now the signal to noise of the received signal, 30 dB to minus 30 dB, plotted as, again, a composite at 20 metres. And so there's a dropout in the middle here, sort of basically signal to noise just drops down, down to the bottom. There are still, obviously, folks still able to get spots happening, but it does take out 10 or 20 dB of your signal. This one's now plotting that data as a function of the solar zenith angle at the midpoint of the path. So as the sun is higher in the sky, the effect on the WSPR connection increases, and so folks that are got the sun high up are losing much more of the signal. And if you're working a path that's got quite a low solar zenith angle, or large solar zenith angle, in this case here, 80 degrees, then you're much better off. So things that are known about solar flare effects, but just something you can get out of the WSPR database.
And the assumption is that D layer is absorbing.
D layer is absorbing, yeah, that's the main thing there. But of course, to some extent, sometimes you can have solar radio bursts that will give you interference, so your signal to noise will drop out. And at HF, these big flares do produce quite strong radio noise, but generally only for a fairly short time, minutes, not hours. So yeah, it's mainly the D region. Okay. I had a look to see if there was anything happening a little bit higher up in frequency. So this is 6 metres. Again, it's the same kind of plot as the others. Relatively low statistics there. Of course, most people are doing WSPR at more in the HF band. Would you expect to see something at 6 metres? There will still be some ionospheric absorption happening there. There'll be other things too, like the solar radio noise too, potentially. But, even though I've got quite a few events there, the statistics don't really give us any indication of anything happening there, but something to follow up on anyway.
Don't you, after a flare, get long F layer stuff on 6 metres?
Yeah, so these are daytime
cards. Yeah.
Yeah, so there'll be other effects following. I mean, once you get some sort of geomagnetic storm happening, there'll be F region effects, but generally, I think not much happening in the F region. There'll still be some enhancement there, but I guess it's the D region that's really blocking it out mainly.
Yeah, you're right. The F is always nighttime stuff.
Yeah, that's right. Yeah. Sporadic-E. So next topic. This is the topic I mentioned a few weeks ago that kind of prompted Justin to ask me to come along tonight. But I went back through WSPR and I built up some VK statistics on Sporadic-E in the region at I've got 10 metres, 6 metres and 2 metres. And, what is Sporadic-E propagation? Well, you can define it based on path length, and that's kind of what I've done here. Fairly short paths that are single hop potentially. And I'll come to actually talking about, all of the human effects potentially on the data and other potential effects. But in that simple approach, here's the seasonal variation of Sporadic-E like propagation, 10 metres, 6 metres and 2 metres from going back to 2009 or thereabouts. I think I've actually only got from 2013 in these plots here. And this is the sort of stuff that you know quite well, the summertime, this is summertime. So these are plotted relative to the 1st of September. I should have put my months in there, but you can kind of see in here, this is sort of January period, and this is late February. So this is all summertime, that's right. Not much happening at 2 metres, but mainly at 6. In here also, I guess you folks know also that there's, other sort of Sporadic-E light propagation at 10 metres throughout the year to some extent.
Did you do any measurements, Andrew, in winter? Because there's a smaller peak in winter.
Yeah, that's another thing to get back to. So I've only gone back to September, so there's the whole rest of that to look at. But the main thing I was really interested in was to check, what's happening to produce this summertime peak here. And for a number of years, I've sort of been looking at Sporadic-E and thinking, is there a connection with atmospheric waves in the upper atmosphere? And so with my background in upper atmosphere physics, and this is a little bit complicated here, but basically you can look at the temperature and the winds in what's called the MLT region, mesosphere, lower thermosphere. So this is around 90 to 120 kilometres altitude, and there's satellite data to help you there. And so what I've done is, on this plot here, this is the climatology, if you like, that Sporadic-E variation throughout the summer. And I've plotted here the temperature in this MLT region, which seems to have a similar kind of variation, and the wind shear. And wind shear is basically, it's the gradient in the vertical wind, so between two altitudes. And the theory tells us that wind shear and temperature have some relation. And I guess what I'm looking at here is, what's happening in the VK region based on the more recent data. And when you do what's called a lag correlation between temperature, this is wind shear, and this one here is the zonal wind, the east-west wind. There are some relationships that are causal. So in other words, the temperature peak is occurring, it's inverse to the wind shear, but it's occurring before the Sporadic-E increases. So it's actually driving that. So these positive lags mean that the wind shear and the temperature are having an effect. So this is kind of like waves in the atmosphere propagating up and causing enhancements in electron density, which are the mechanism for the Sporadic-E.
The purple graph is derived from WSPR, is it?
So this blue one's derived from WSPR. These three are derived from the satellite measurements, but they're correlating with the WSPR signal. Yeah. And then when you look at days when you don't get Sporadic-E in the summertime and the days that you do, when you separate those out, the days that have the Sporadic-E have a higher temperature by a few Kelvin. The ones that also have the Sporadic-E have a stronger wind shear as well. So that kind of works in the physics there. So I don't think anybody's really done a detailed study for the VK region, so I'm kind of keen to move that through, see if I can add anything to the literature there. And then another topic I was looking at, because I'm kind of interested in seeing if I could hear anybody in the Antarctic occasionally, and also see auroral effects at HF. So I've used the WSPR database to look at short path connections at high latitudes. So this is kind of a map which is colour-coded according to auroral activity. You can read that scale down there. The brighter the colour, the stronger auroral activity is, and that's measured by this index called the Auroral Electrojet Activity Index, which you can get from that site there. And you might be asking, why are all these sort of strange spots happening there? Well, I sort of scratched my head a bit, and then I looked at the call sign, and this is the Polled Stern, the German icebreaker on some voyages, and Neumayer Station in particular, making contact. There probably are some false spots in there as well. This is the other problem with WSPR, is knowing what is the percentage of false detections. We think it's small, but in the scheme of things, there are, can't quite recall the number, but it's about 10,000 paths here. A lot of them are just, you know, between fixed points. And these actual oceanic ones, they're quite a small percentage. But the point here being that there's a lot of activity between Australia and Africa, and some in South America. So I was kind of having a look at what you could see on those paths. And the sort of the quick summary is that I was a bit surprised, but basically there's a bit of an asymmetry in the signal to noise along this path when there's auroral activity. And I'll show you. So this plot down the bottom left there, this shows you essentially the effect on VK to Africa or Africa to VK, depending on auroral activity. And not surprisingly, when you get more auroral activity, more disturbance, more absorption, and the number of spots drops off as the auroral activity increases. But what was surprising is some asymmetry in the signal across that path. Now, this plot down here is the power distribution for VK to Africa and Africa to VK. Australians tend to use lower power, it seems. I guess we're a little bit, we've got perhaps a different audience out there. The poor Africans probably, they're a bit more isolated, so they seem to be transmitting generally at higher powers.
Might have something to do with the regulator.
Because they can.
Yeah, that's right. They probably can. I was kind of wondering, what the reason is. So I was speculating, but
That's only the difference between 20 watts and 40 watts.
yeah,
We're
that's
not
right.
talking.
Not talking hundreds.
Yeah.
No. So it's still in the realms of.
No, but as in, that's not
Yes,
because they
that's
can run more power than us.
Yes.
This plot here is when you look at the signal to noise. So this is, the blue is VK to Africa. So generally, when it's coming back the other way, because they have a bit higher power, we tend to see perhaps better signal to noise on the upper end there. So there's a bit of an asymmetry there. And when you correct for the power, if you sort of subtract the transmitter power from the signal to noise, you get more of a symmetric distribution. But there's still a bit of an excess. It's quite small, which sort of suggests that when it's coming back the other way, we see a higher signal to noise in general. And when I looked a bit deeper into this, when I started to filter it with auroral activity, so this is the raw signal to noise for different auroral conditions up to extreme, and generally when it's an extreme auroral activity, we tend to see much higher signal coming back the other way from Africa. The Africans, we tend to drop out. We tend to get sort of blattered by the auroral activity, but we see this distribution. If we correct for power, it's a little bit different, but there's still this asymmetry, which these bars all add up to unity, just for different auroral conditions. But there's an excess of connections coming back the other way during large auroral events. And so it's actually, if you want to listen, so I think basically what it's saying is, if you want to listen to African stations, the higher the auroral activity, you'll still see more of them than they'll see of us. There's a small asymmetry when it's quiet, so And I think that relates to refraction and scattering by the auroral edge of the auroral oval, the way it actually is displaced. And of course, generally when this is happening, it's nighttime. In fact, what I've filtered is nighttime for these paths. So there is nighttime between Australia and Africa, but there's this interesting asymmetry where we tend to see more of them than they see of us. I don't know if that's been described in any amateur journals or otherwise, but I'd be interested to know if anybody has any insights into that. And then the final one, solar proton events. And the Antarctic folks know a lot about these because when we try to do HF comms in Antarctica, if there's a storm of protons hitting the Earth, it impinges on the high latitudes and increases the absorption at HF quite strongly at the lower frequencies. So I looked at paths that were connecting Australia to Africa, and the blue curve here is the conditions prior to a proton event, and then the red is actually during the event, and it's taking out about 5 to 10 dB here at 10 megahertz, and you could do this at lower frequencies as well and see the effect. But that's a useful way of actually looking at some paths that would cross through this region where the protons are actually increasing D region ionisation. So some of the things I haven't talked about there, of course, is one of the other problems with WSPR, I guess, is knowing when people are transmitting but not being heard, and that's interesting information as well. And then there are false decodes, of course, which I guess one could filter on signal to noise. Generally, they tend to be the weaker ones, I think, but it'd be interesting to know. Of course, you can look at where the stations are located and do some reverse lookups and filter those out. But I'd be interested to know if anybody has some feeling on that human effect there. Here are some other things that you can actually have a look at. In fact, I've looked at all of these. I was interested to know, how do you know when you're seeing a short path signal versus a long path? And there are some clever ways of sorting that out. And if you're interested, I could tell you what I've done there. The problem is actually I've seen so few long path VK, confident long path VK detections, that there are just very small numbers there. But you look at the maximum usable frequency along the path and decide whether it's coming from the short or the long. I talked last year about the Space Lab experiment I was involved in, ionospheric holes, and I've had a bit of a look at ionospheric holes in the New Zealand region using WSPR from the launches in the North Island, the Rocket Lab launches. There have been 73 of those now, so there's a good database, and it's actually getting a connection from Australia through where the rocket's actually flying to New Zealand or other paths. You kind of want to have a connection where the maximum usable frequency is near the frequency that's being worked. So got a few statistics on that, but nothing obvious yet. Tropospheric propagation, I'll say something about that just on the very last slide. And solar eclipse effects. There's an eclipse coming up, a total solar eclipse over Australia. Folks in the Ham-Psi group have done quite a lot of work looking at ionospheric effects of solar flares on digital modes. And global geomagnetic storms. So this is 20th of January this year. This is from the WSPR rocks propagation chart, showing the activity on a whole range of frequencies here, but a big dropout, 40 metres and that's 20 metres just for a few days, and then a pickup. So that's kind of interesting to see that.
And can I just say that the Whisper Rocks is actually Phil Barnard, VK7JJ, up north. He actually created and looks after that database. So that tool, and it's the top of the list of the tools if you go to WhisperNet. So yeah, it's excellent.
Yeah,
Really good.
When Justin asked me about the wind shear the other night, I thought, oh yes, Hepburn charts. Can I reverse engineer them? And so Hepburn is using data from the Canadian Weather Service, and I've got some of that data. I'm just comparing my version of the Hepburn chart, the Klekociuk chart. I don't know, but I can certainly see the strong ducts here. But I guess it's the intermediate activity. But there are patches here where there are ducts at certain heights in the lower atmosphere. So there's a map of the duct height, which Hepburn doesn't show us. So this might be an interesting thing to develop a little bit more, because what I'd be interested in doing is actually verifying this using Whisper. So if we can determine tropospheric ducting activity, I guess it's based on perhaps the distance of the path. Certainly, there are transequatorial propagation paths as well, but it'd be interesting to try and verify this. So I don't know if anybody's really had a good dig into verifying the ducting maps. And, I know Rex has done some work here using radiosondes, and but if we can use Whisper.
Yeah, I've been just using the atmospheric models to get the height of the duct.
Yeah, that's right. So
Was it mainly Whisper, Hepburn for the 10 gig across to New Zealand? Was that?
Yeah.
okay. Yeah.
It was actually the year of the bushfires, which I produced.
I remember that.
Yeah,
1990, 2019.
Yes, one of my friends went to Hawaii.
Well, interesting. The smoke might have enhanced that. Well, the water vapour in the lower atmosphere. But anyway, so if anybody's interested in following that up, I'd be keen to try and verify some of the forecasting using that approach. I'll talk to Rex a bit more about his approach there. Anyway, so just a few ideas for
So
science with this.
you're talking about, Andrew, basically proving that Hepburn, that there was a duct there? Is that what you mean?
Yeah, I guess it's seeing if those categories, the lower categories here,
You actually
stack up. Because if you look at the physics, the strength of these ducts outside this region is a factor of 10 to 100 smaller. The refractive index is very small in this black region here. In fact, I think I'm using the same physics, but I have to stretch the very tiny values that are in this region here to a very large extent
to get something
to
like
get
that.
something that looks like that. Yes.
Because I know Richard and we've done a couple of tests across the VK3, haven't we, from Mount Wellington? And it's varied from fair, so that blue, and it's been reasonably strong. And then we've gone up other days and it's said that it's supposed to be extreme, and it's not been as good as when it was fair.
Yeah.
So it's kind of interesting to sort of see the correlation between what's actually a super strong duct and you get not a lot, but then a fair duct and you actually get a lot.
Unless it's affected by the height.
Might be affected by the
Yeah.
height, and also I think
Yeah.
it might also be affected a lot by the fact that we're pretty inland, because we've got to go across the whole of Tasmania to
True.
get to Bass Strait.
Yeah.
Whereas if you're sitting close to the coast up there, it probably is very strong.
That's like with Launceston's RAA repeater. They get ducked quite a lot, where they get VK3s coming in from across the water. Like I remember one day there was a really strong duct the whole day, and I was talking to this VK3 station on and off the whole day. I was absolutely surprised. I think it lasted 2 or 3 days actually.
Right.
Because we were connected to RAA up in Launceston, and then the VK3 was coming in via RF direct from somewhere along the coastline of Victoria over the Bass Strait to RAA, which was really surprising. So some days it comes in real strong, other days, like Hayden said, it varies.
Yeah. Well, being able to reverse engineer the maps, or at least know the physics that's going into them, one could actually look at point to point and do some ray tracing, rather than just looking at a
11.6.
general map. So if you're interested in particular paths.
11.6.
Thank you.
So can you, with your heights,
Yeah.
is that a prediction of the height of the duct?
That is a fairly solid. It's based on the forecast data. So, but one could use analysis data. So we're using all the radio sondes and other information, the satellite water vapor and so on. And so you could go back and look at past events, which might be more interesting.
Because I was interested in future predictions. So, like, if you saw that the height of the duct was at a certain height at maybe each end, then each station could go to potentially that height and get into the duct if they
I
can.
think that's what we've discovered before, is that the Hepburns will tell you when there's a likelihood of the duct forming. You sort of got to go. And I remember when we were doing that stuff across to New Zealand on 10 gigs at different heights.
But we've got the radio sun here in Hobart.
Yeah, but it was interesting how the Hepburn, you could predict when it was likely to happen, but then after the fact you could look at the radio sonde data and then actually tell you what it was after it's gone.
Yeah.
That is the problem with the radio sonde data, though, is it's only like twice a day and it's probably long gone by the time you get the data in. And
I guess some other things there. So the forecasts, they're generated sort of, hourly or 3 hourly, depending on which meteorological service, and they'll be fairly accurate still. They'll follow the sonde. One can compare, so you can still use forecast data, get a vertical profile. But I guess once you've got this sort of map, you can then check to see if there are any holes in the propagation path, if there's going to be some sort of loss process happening. And get an idea of how consistent that propagation might be. So, it'd be interesting to follow some of those ideas. As I say, point to point would be interesting rather than just looking at a general map. Do some point to point.
Andrew, are ducts at typically similar levels, or are they right up?
Yeah, well, these ones here in that plot, if we can go back to that one. They tend to be higher at the lower latitudes. Now, I guess the complication is that in this data set here, which is the same, we think, when I say we, co-pilot. How many personalities does co-pilot have? That's the other question. This is only using 1,000 hectopascals is the lowest level, or the surface. And in fact, some of these ducts are below the 1,000 hectopascals. So this is actually duct height in metres, and you can actually see some numbers here which are negative, which just means that they're below the 1,000 hectopascal height. But generally at the higher latitudes, they're lower in the atmosphere, and these guys are higher up.
Because when we see a forecast as amateurs, the thing that we want to know is, do we drive to the beach or do we drive to the highest mountain?
Yeah, that's right, exactly right.
Or do we drive halfway up?
Halfway up, yeah.
Yeah, well, it sort of suggests here that some of these heights are only a few hundred metres relative to the surface, wherever that may be. And that's something I should put in here, is actually the geopotential height of the duct, not the height relative to the lowest pressure level.
So really you need to correct those figures to what the actual atmospheric pressure is for the
That's
night.
right.
So if we've got a big high over, for instance, 1,030 or some such, then that's going to make quite a significance to us. 1,000 millibars.
It could do. I didn't check to see what highs and lows were sitting in here. This is just for the other day. But yeah, I mean, they could still be fairly low. So going up the mountain might not be an advantage.
Other questions for Andrew about the presentation? Any specifics?
Are you going to continue working on your modelling and refining it a little bit? And
Yeah.
I find that interesting that because we spoke beforehand about how you're saying it's Australian data and it's probably a lot more curated for us rather than
If we can use the
Canadian
access model, which has got more tuning for the region, that's handy, and that's available. There's plenty of meteorological data out there. This Canadian one, I mean, it's similar to the other lot. They go out to 120 hours forecast, and they're updated every 12 hours. So,
The other lot being F5LN.
Yes, that sort of thing, yeah.
And we had a look at that just before, so...
Yeah. It appears to be different. It's just that it's a different colour coding levels.
Yeah, that's right. I have to go and have a look to see what stretching is done. And that's the thing, I don't really know if, having a factor of 10 or 100 difference in the duct strength, how does that translate to the ability to make a connection or the signal to noise you might get or something like that? So, yeah.
Okay, cool. Very good. Any other questions for Andrew? I'm going to open it up. Who can we do a bit of a straw poll? Who's used Whisper and contributed to the database? Can I get a bit of a feel for what sort of frequencies you're using it on? HF, VHF,
VHF.
VHF?
2 metres.
6 metres.
6 metres.
Yeah,
40
6
metres.
and HF.
40 metres and 10 metres.
23 centimetres. Done it on 23.
Okay.
It's a bit problematic at 23 centimetres.
Starts scattering.
Because the tone spacing's too narrow for chopper scatter.
Yeah. Okay. And you made a good point last night around 6 metres. The 2-minute cycle for Whisper is too long.
for Sporadic-E, yeah.
It's all been and gone.
It's gone. It's absolutely gone.
It is very good though for meteor scatter because if you actually sit there and listen, you'll hear a ping.
Yes.
And if you hear pings, then you can then switch over to meteor scatter.
Yeah.
Because it's such a long transmission.
So, but you've got to be there.
You got to be there listening. Yeah. You'll see it on the waterfall. They'll be really bright.
Yeah, I've seen
Ping.
that.
Yeah. And if you've got the averaging on your waterfall, you'll see it come up and then it will slowly dissipate down.
Yep. Okay.
What was the purpose of Joe Taylor gathering all this data? Why has he done it?
Well,
So you can come along 20 years later?
I hope so.
To be
because-
fair, he didn't do it for gathering the data. He did it as a propagation tool.
But other people,
And then other people have built the database around it.
And pull the data out.
Yeah.
And store
yeah, I guess maybe there's more radio amateur interest in the database, but folks like me come along and try and apply it, I suppose. Yeah, but I encourage people to keep contributing because there's some interesting stuff in there. But I guess maybe some of the stuff I've been doing is kind of like the stuff they did in the 60s and the 50s, on seeing space weather effects. But you can do it in a different way now, and there's other information that you can build into the picture.
You can imagine if they had the database back in the 60s.
Oh, that's right. Yeah, sorry.
Oh my goodness.
It's the same reason, Greg, why Joe Taylor, he developed FT8 for 6 metres because it's a short transmission time, so it's effective in Sporadic-E. But then everyone took it and started using it on HF. It's unintended purpose. So I guess, he builds one thing and people use it for other things, which is kind of cool.
Yes.
Keep reminding us it was for 6 metres.
Yep. It's because no one uses it on 6 metres.
FTA?
FTA.
Well, not enough people use it on 6 metres.
I would have thought There's no SSB left on 6 metres.
Almost exclusively FDA.
There's a little bit of SSB.
Absolutely.
A little bit of SSB.
So, any thoughts about and uses that you've found for Whisper, for propagation, for other things? Like, what's your thinking? What's your feel?
One thing I've been using it for is aircraft scatter, and on 2 metres.
Okay.
And there's a guy, VK3 ZTE, seems to run Whisper on 2 metres pretty consistently.
Okay.
And I can see the aircraft each time. The trouble is he's probably only running 20% of the time random rather than all the time, which would make it more interesting. But that's about 650 kilometres. He's up in northern Melbourne on 2 metres.
Do you know what antenna he's using?
No.
Omnidirectional, I'm guessing.
Oh, no, I wouldn't have thought so.
So he's pointing at you?
Well, we're not talking to each other, so he doesn't know that I'm around, and except if he looks on the Whisper database and sees stuff.
But if he was pointing at New Zealand, you wouldn't get anything?
I wouldn't have thought so, no.
One thing I do use Whisper for is antenna testing.
Yeah.
When I create a new antenna, I put it on Whisper on the designed frequency and let it go for a week and see what is hearing it and what I'm hearing. And it's fascinating.
Yeah.
Because it's not only telling you obviously what you're hearing and how strong you're hearing it, but also if you dig into it, patterns and all sorts of things, if it's a directional antenna.
Yeah.
So I have found it absolutely invaluable for antenna testing.
You'd need a reference antenna, wouldn't you?
No.
You just want to know if it works.
I just want to know if it works, absolutely, and how well it works. That's the and okay, you could do an A/B.
That's what I thought you meant.
So create the antenna, do the tweaks, do another week, see whether it's improved or it hasn't improved, etc. Now you're also assuming that things in the atmosphere are doing the same same thing, but okay, you can make a judgment there. You can make a judgment call there. But absolutely worth its weight in gold for that sort of stuff.
Which way do you normally aim it?
Well, in the case, and that's an interesting point. When I first built the mag loops, it was north-south, and I just left it on north-south, and then I actually put it to Europe and I put it to the States. That was the next 2 weeks, and just proved that I'm actually hearing more stateside stations, or I'm hearing more Europe stations. I'm actually proving that it's got a bit of a directional characteristic.
I was just curious if you had a reference direction when you're testing new ones.
Oh, no.
So when you pointed it to Europe, you didn't get any US?
Oh no, you get other stations, but predominantly it's Europe stations, and predominantly it's US stations. It's that sort of stuff. You always get everything else because it's not the mag loop's not that tight. It's a donut.
I think the use of the data is really good, not necessarily Whisper, but like with PSK Reporter, where it gathers all of the transmission types.
Yes.
And you can sort of go, show me all of the 6 metre activity that my station's heard, or that Justin's station's heard, or, Hayden's station's heard. Or, the really cool one on 6 metres is show me what VK's heard. Show me all the activity. It's only the last 15 minutes.
Yep.
But sometimes it's very demoralising because you look and you'll see everyone from about the middle of Bass Strait north is working all this wonderful DX, and we're not.
Nothing.
Well, can I just point out that Richard was Richard the other day was madly working. What was it? Europe. And nobody else was.
Italy and France.
But anyway,
Italy and France. It was
luck of the draw.
just happened to. sitting on the couch and my phone goes, just been heard by IW5. I'm like,
I
in
got
6
that later
metres.
too.
Yeah.
I might just
Up
go
to
upstairs and turn the antenna towards the west.
Well, that sort of reminded me of something Martin mentioned, I think, at the conference, you know, about these weird propagation modes that can pop up, you know, long path unexpectedly and things like that. And that's where you can use, well, any of that, PSK reporter.
Yeah, well, and one thing you were talking about long path, short path. My experience is that very often they're both there.
Yes.
It's just that the long path
It's,
can be 20 dBs louder than the short
okay.
path.
Can be louder, yeah, okay.
Very, very much more louder until they change over,
Yes.
then the other one becomes
Angles
louder.
change.
So it'd be hard to tell which one you're receiving.
Right.
I guess if it's very loud, it's probably long path, certainly from Europe.
Yeah. Okay.
And we used Whisper to look at the difference between stations in the country and station in the city, where we're looking at the signal to noise, and it was quite dramatic.
Winston had his station out at Orford, which
The remote
was
station.
much quieter.
I've got a remote station out just north of New Norfolk,
Mm.
and you know I can turn that on at home, and I have to flick the antenna switch to be sure that I've got the antenna connected.
Right.
At home, you turn it on and the S meter goes bang.
Yeah, that's right.
Yeah.
So there's a massive difference.
40
And
miles.
Like
you
we were on
get-
top of a
With
mountain.
Whisper, you can actually put a number on that.
Yes, that's true. Yeah.
Is it connected? Isn't?
The Whisper database is really handy for, especially Rex has probably done this too with tropospheric ducting. And if you've got another station at the other end who's consistent in their transmissions, the one I think of is Bob ZL1RS was running a 2 meter Whisper beacon back to VK, and I think he had 2 beams. He had one alternating between beaming towards Queensland, Sydney area, and then one further south towards Victoria, Tasmania. So he'd alternate between the two, and you could watch it over time and then go back and filter through and look at the signal strength and how it comes up and then fades away, and you can correlate that with times of the day and the weather and everything else, which is really handy to sort of get a sense of when's the best time to be, you know, setting up and getting on the air. But then also we then use the 2 meter data to then go to say a high band and try a high band, and then all of a sudden we'd find that high bands were stronger than 2 meters,
Right.
Mm.
and then sometimes it would flip. And I guess that's just the size of the duct and everything else, and
That's right.
the power levels and the antennas and
You
all
get
sorts
that
of
wicked
things.
QSB as well sometimes on the duct where when we're on the mountain working into VK3 on 3.4 gigs or whatever, you get really, really strong signals, and over a period of minutes it will drop right off and you think, oh, it's gone. You'd be like, oh, but then you listen and you tune to a beacon and you hear it come back up again. So and some of the differences between the peaks and the troughs would be like amazing.
And not very far between them.
Sometimes it would be quite quick, and sometimes it would be very, very slow, such that you think, if it's all finished.
I've found 6 meters Whisper is good for domestic, to see propagation domestically, because it tends to be strong enough to last long enough when it's especially in the peak.
Yeah.
But over international paths, I know a lot of people beam like towards North America, and they probably get 1/50th of the amount of signals because there's not Sporadic-E hops along the way. There's probably F layer and everything along the way. So by the time maybe if an E cloud is getting you into the propagation, the F layer further along, if the E layer drops, then you lose your signal halfway through your 2 minute transmission. Whereas in FTA, you can make a contact in 45 seconds.
That's right. Yeah.
So you can actually you'll see heaps more signals,
Yeah.
which is very handy domestically though, and you hear it in the speaker as well. You'll see the S meter just start pinging towards the right.
Yeah, I've had a bit of a look at. I must compare my Sporadic-E detection with the FTA type stuff as well, because that would be interesting to see. If that holds up that pattern. It does seem reasonable.
I don't know if you can capture FT8 data because it seems to get sent and then it sort of
It disappears.
disappears.
Yes, that's right.
Correct.
Yeah, I have been running at home an FT8 logger just to pick up stuff, but yeah, I like using 20 years of data rather than just 1 year or 1 month or something. Yeah.
Absolutely. We've got a few people online. I just asked the question: what are people using Whisper for? Ben, HF reverse beacon purposes, so mainly on HF, 6 and 2 meters from Jeff, VK3 GBE, 6 meters propagation predominantly from Darren up in Mount Isa, and 6 and 2 meter opening. So now, Matt, VK7 MAT, big thank you for the presentation. What's the most underrated solar factor that radio operators often overlook but should be paying more attention to? Great question, Matt. Great question.
I think that solar radio noise is a bit of an interesting one. I've seen on my home system, I'm getting saturation at times on my HF.
So it's solar storm.
Solar radio noise storm, yeah. Some of those can be only very short. So type 3 solar bursts can be literally seconds to a minute or two. Okay. But type 2 events last a bit longer. But yeah, I guess that's a short term. So just knock out a few spots, I guess. That's the thing. We'll
so did you see a real peak in that January event?
That was, I saw the type 2 burst. From that, which is a descending, it's a dispersed signal coming down from high frequencies to low frequencies.
Okay.
I guess generally, you'll only see those signals above the ionospheric cutoff frequency. They won't penetrate the ionosphere if it's too low in frequency. But I think some of that solar radio noise can be very intense, and it might confuse you a bit at times if you're listening and got this sort of roar in the background. I don't know if many folks really hear that, but
certainly hear it on 6 meters.
Right.
It's a very wide band.
Yes, it's can be gigahertz. But at HF, because it's dispersed, you'll only occupy maybe 20, 30 megahertz of frequency at a time. These bursts are propagating out through the solar corona.
11.9.
And they're
11.9.
They're dispersed in frequency, and there can be many seconds delay between, say, 6 meters and 20 meters.
I'm interested, Andrew, too, with your, because Sporadic-E to me is like probably the most fascinating form of propagation. I think it's there's been so many different theories, and I think the consensus is that it is definitely wind shear, because I think people said like thunderstorms and all sorts of things contribute.
They can make gravity waves that propagate.
Yeah, gravity waves as well. One thing that interests me with looking at your years of data, and you showed the graphs where you had 10 meters, 6 meters, 2 meters. Obviously, the higher in frequency you go, the less often it occurs. I think 2 meters is like 10 times less than 6, and I can't remember what it is, 6 to 10. But do you see any correlation with specific times of the year when, say, 2 meters is like, that's the hot spot of 2 meters, like the peak of 2 meters? Is that any different than, say, 6?
Yeah,
or is it any different than 10?
Yeah, I haven't looked at that. It's an interesting way of slicing it up.
And I don't know whether you could filter it, but you probably could. It'd take a bit to do. AI could probably do it.
Yeah, that's right. 5 seconds.
One thing which would be interesting to do is with your data set is taking, especially on 2 meters, where the paths are, or where the hotspots are for stations.
Yes.
So, like from experience, I think from VK7, VK4 is usually the best place from here, because it's a single hop.
Yep.
And when the Sporadic-E cloud is sitting over about Canberra and it's intensely strong, that's when we get the best propagation to VK4. I mean, it's obviously going to be it's obviously going to be populated areas that are going to be the main ones.
Roger's slower.
Yeah. But it can, it'd be interesting to correlate. did the VK4s see more propagation than us?
Yeah, that's
Did the
right.
VK2s
Yeah.
more than VK5? All that sort of thing.
Yeah, it's an interesting way. Yeah, I definitely can make maps like that to
Mm.
look at the hotspots and compare the
A
different.
lot of these things, though, are self-fulfilling because people are aware that there's a hot
Yeah,
spot,
so
so they
they
all
go
come
look.
on.
Yeah, I know.
Yeah,
Yeah.
that's right.
The PSK reporter will show you that too, because you can actually see in the last 15 minutes, even though that's a correlation between what people are working and also what people are
Well, that's what's made tools like Whisper and PSK Reporter really good, because it makes everyone aware that it's happening. I don't understand how back in the days of when you only had CW and SSB, how people made these long distance contacts.
Because people used to sit there at their radios
All day. And rely on beacons, I suppose, as well.
Beacons.
like
I can
Morse
remember
code beacons.
Ian Philby over there, who was a 6 metre sort of guru. He used to work at home and he would just have the beacons, scan group.
Ah.
He would just be doing things on the bench and he'd sort of go, oh, what's that?
But he also
Interesting
used to use
F1
visual
television on
beacons
your
because
own
he would always
yeah.
have. He would always be
TV.
listening to Channel Zero in New Zealand, and whenever you saw the TV change
Yeah,
started
the
to change
NUF
a bit,
started to rise. He'd sort of go, oh, what's going on there?
Yeah.
He used to live it and breathe it. It was amazing.
There is one interesting time of year though that I forgot to mention
Visual
on one of the
beacons.
slides, and that's around about the end of January, where there's actually a drop in Sporadic-E, if I remember rightly, and there's actually a sort of a 2-week period where it does significantly drop out, and that's related to a process called the 2-day wave, which is an atmospheric wave that happens every time around that time of year, and it changes the wind shear in the MLT region, and that pops up in one of those plots, and you can kind of see where it dips out a bit. So that's kind of a time when you might see less activity.
Because I think the conventional wisdom was always almost Christmas Day to like New Year's Day was pretty much the
The
peak.
best.
Yeah.
That's because everyone was at home.
Well, that is. Have you ever noticed?
It's that self-fulfilling prophecy again.
Have you ever noticed Saturday morning, the amount of 6 metre spots that you will get is ridiculous, because it's like Friday night overseas and Saturday morning for us, and everyone's on the radio.
Yeah, well, the climatology plots I showed tend to show a later peak for 2 metres, I think, than
All right.
6 metres. By a few weeks maybe.
That last opening was actually on February the 1st. 6 minutes.
Yeah.
One of the other things I looked at was year-to-year variability, and it looks like the Antarctic vortex, stratospheric vortex, has an effect which varies from year to year. And of course, this year we've had a disturbed vortex in a weird summer weather season, and that's pushed the peak out a little bit in time, I think. So I'm having a bit of a look at that too. That helps generate these waves that cause this wind shear. So.
If you know anyone in Antarctica that can bring a 6 metre beacon, Whisper beacon down there, we'd love to get
That'd be
one down there,
interesting,
because that would be
Wow.
excellent to
Better
propagation tool.
I think keeping the antenna up in the air would probably be the
Yeah,
biggest.
that's the
Yeah. Oh, well. Any final questions? Comments? Can we show our appreciation of Andrew?